Okay, I think it's time to start now. Hello, everyone, and welcome. This is Adel Tahir. I'll be the moderator of today's webinar, titled Understanding Reservoir Fluids and PVT Modeling, presented by instructor Engineer Muhammad Ala. Engineer Muhammad Ala is a highly accomplished petroleum engineer with over 13 years of specialized experience in reservoir engineering, particularly in gas condensate fields and unconventional reservoirs. He is currently serving as a senior reservoir engineer at Khalda Petroleum Company, a GV with Apache Corporation. He leads multidisciplinary teams in reservoir management, integrated field development, and advanced reservoir simulation. Engineer Muhammad has a proven track record in equation of state modeling, leveraging tools like PVT to build and validate fluid models for complex reservoirs. His expertise extends to pressure transient analysis, production optimization, and reserves estimation, with hands-on experience in softwares and dynamic modeling tools. Before we start our session, I'll just make a small presentation about OPA upcoming service and plans. Our next course that will be conducted this Saturday, 3rd of May, titled PVT and Equation of State Fluid Modeling, that will be presented by the same instructor of today's webinar, Engineer Muhammad Ala. Its price is $200, and there is an early bird discount for the first 5 registrants. You will get 10% discount on it, so you will get the course for only $180. You can scan this QR code to register in this amazing course. We have also completed more than 50 live course, which is now converted and available as recording sales in different disciplines like reservoir engineering, G&G, rig and rigless operations, production technology, safety and data analytics. You can check all our 50 courses if you after scanning this QR code. You will be redirected automatically to our website where you can access everything. I will also send all the links in the chat after I end my presentation, so don't worry if you couldn't catch up on scanning this QR code. One of our best services, which is a mentorship program, it's a one-to-one mentoring sessions by highly experienced mentors. It's like a tailored program based on your needs. You can request practicing on how to produce output results from software, guiding on personal data, professional guiding for PhD and master, helping undergrad students in their projects. We have completed more than 50 mentorship program with more than 950 learning hours, and the mentees were from more than 10 different countries. You can also scan this QR code to register in our mentorship program. Here's a glance of our OPA website. It's www.opacourses.com, where you can access everything we have talked about, like enrolling in our recorded courses, enrolling in our next live courses, registration in our free webinars, internship, mentorship, everything you can access it through our website. So make sure you wait a visit. So how to be an OPA ambassador? There are 2 tracks to join our OPA ambassadors community. Take 1 or more courses or take a mentorship program. So what will you get from being an OPA ambassador? You will get discounts on all courses in the future and group discounts when you invite your colleagues. Thank you for listening, and now it's time for our session. Engineer Muhammad, you can share your presentation now and start.
Thank you, Mr. Adel, for this quite wonderful introduction. Hello, everyone, and thank you for joining today's webinar, which will be about understanding the reservoir fluids and PVT modeling. I am Mohammed Ala, a senior reservoir engineer working at Khalda Petroleum Company that is located in Egypt. So let's begin today. I want to share with you the presentation first. Okay, do everyone see the presentation?
Yes, it's clear.
Yeah, okay, thank you. So today we will explore the nature of the reservoir fluids and know how they behave under varying pressures and temperatures. And we'll answer why PVT modeling is essential in predicting the fluid performance across the production systems. By the end of this session, I hope you will have a deeper understanding of not just the theory, but also the practical importance of the fluid characterization. So let's keep going in the presentation and define the reservoir fluids. They are complex mixtures of hydrocarbons existing in dynamic state influenced by extreme pressures and temperatures. They do not behave as pure liquids or pure gases. So whenever we are talking about a hydrocarbon mixture, do not relate the behavior as the liquids such as water, because water is a pure component. It doesn't act like the hydrocarbons. So they show properties of both phases shifting continuously as conditions change. An important point to focus on, and keep that in mind, no two crude oils are identical because the composition is like the person's fingerprint, so you can't replicate it. And by that, each sample contains unique proportions of various hydrocarbons and sometimes non-hydrocarbon components, resulting in a very distinct physical behaviors. So for that, we classify the reservoir fluids into 5 main types. The dry gases, which are found as a gas phase at the reservoir conditions. And what we mean by the reservoir conditions is the pressure and temperature, and they will not condense any liquids during their path of production. While the wet gases behave like dry gases inside the reservoir, however, during the path of production and temperature change, they will condense liquids. So they pass through the dew point curve. And we will know about the dew point curve and the bubble point curve in the following slides. So let's move on to the third type, which is gas reservoir gas condensate. At the initial conditions, the fluid is found in a gas phase normally. However, during production, the reservoir pressure starts to decline. And as we all know, the temperature remains constant in the reservoir. So during that, there will be liquid condensation inside it. In order to differentiate between the three types of the gas reservoirs, we can relate to the capability of the fluid to condense liquid. So it comes very easy. If the reservoir fluid can condense liquids inside the reservoir, then it is a type of gas condensate. And if not, then it's either dry or wet. For the oil reservoirs, there are two types, which are volatile and black. For modeling purposes, I like to differentiate between these two types by relating the type of the evolved gas below the bubble point. As we all know, the oil, when hits the bubble point pressure, gas starts to evolve from it. So if this type of gas is gas condensate, then it's a volatile oil. However, if it's dry, then it's a black. In order to understand the behavior of the reservoir fluids, we need to relate to the phase diagrams because it provides a powerful graphical representations of how fluids behave under changing temperatures and pressure. So here on the presentation, there is the phase diagram of water, which is a pure substance. So let's start with it. And as you can see, if you have a cup of water at the ambient conditions, such as an atmospheric pressure of 1 and normal temperature of 20, okay, you will find water as liquid phase. If you try to boil the water and exactly at 100 Celsius, then it starts to evaporate and the phase will change from liquid to gas. So this curve represents the vapor curve at which the phase will change from being liquid to being in gas phase. And oppositely, if we try to freeze the water, then actually at 0 Celsius, it will start to freeze and the phase will change from liquid to solids, which is represented by the ice. So understanding the two curves, the vapor line curve and the melting curve, helps us to imagine how the phases will change with different pressures and temperatures. As you know, the hydrocarbons are multi-component systems. So let's imagine from where the phase envelope appears. If you have a two-component system, which consists of methane and ethane, and there is a mixture between them, and if you try to draw the methane vapor line, and so as the ethane, then you will find that at this condition here, the methane should be in the gas phase. However, the ethane should be in a liquid phase. And from here, we mark the phase envelope, where this region represents the two-phase region. So the phase envelope consists of three main points: the bubble point curve and the dew point curve, and the intersection between them, which represents the critical point. So to make it simple, to the left of the critical point and outside of the phase envelope, then you will find 100% liquid. And to the right of it, okay, you will find 100% gas, while inside it, you will find two-phase region. And the point of pressure and temperature will be determined by the control line like this one. So it shows that 75% of the composition is liquids and 25% is gas. Moving on, if we change the pressure and temperature, so let's take this point, then you will have 25% as a liquid phase and 75% as a gas phase. So understanding the multi-component system, such as hydrocarbons, then we develop the understanding of the phase change with the pressure and temperature. Let's take an example that illustrates the change in phases due to the change of pressure and temperature. So here, this phase envelope represents composition, a certain composition, and we are going to play with it. If we have our initial condition, which is represented by a reservoir pressure of, let's say, 3,500 psi, and temperature of around 300 Fahrenheit, so our point will lie nearly in here, because this is the temperature and this is the pressure. So this is our initial condition. And because we are to the right of the critical point, then we will have a gas reservoir as a single phase. And we want to test which type of gas is this. So let's make two tests. The first one is to decrease the pressure, maintaining the temperature, and see whether condensate will start to condense or not. So the direction of the pressure is that way. So when decreasing the pressure, we will not hit the dew point and will not enter the two-phase region. So by that, it's either a wet gas or dry gas. The second test is to test whether point A2, which represents the separation conditions, will have condensation or not. So during the path of production, as we can see, we will hit the dew point curve, and this marks entering the two-phase region. So it's a wet type gas. So let's assume that our initial temperature was not 300 Fahrenheit, it was about 100.
We are aware of this issue. I will contact an instructor to check with him. I'm sorry for that. Yes, there is a problem with the instructor connection. So he's trying to reconnect again. So please wait for 2 minutes until he fixes this issue. Okay, so until the instructor fixes this issue, if there is anyone has a question regarding this first part, please type it in the chat, and when he comes, he will answer it immediately. So, is there any questions until he comes? Okay, for the recently joined attendees, there is a problem with the instructor's connection. He is trying to reconnect, and then we will continue. And we are sorry for this inconvenience. Okay, he's here now.
I'm sorry, everyone. I don't know what happened. But anyway, let's continue.
Okay, please.
Okay. So we were talking about the phase diagram and the phase relation with the pressure and temperature. And as I was saying, if our new points were the reservoir pressure of 3,500 and the temperature of 170 Fahrenheit, then our point should lie just above point B in here. As you can see, this is 3,500 psi, and this is around 170 Fahrenheit of temperature, okay? So because we are to the right of the critical point, then we expect that the reservoir pressure will be a gas condensate reservoir. And what we want to know and identify whether the type is a gas condensate or wet gas. So what we are going to do, we will make our first test to deplete the pressure while maintain the temperature. So we are mimicking the reservoir performance. And as you can see, while we are going down, we will hit the dew point curve. And by hitting the dew point curve, the first droplet of liquid will start to condense. And by that, we have a gas condensate reservoir, not a dry gas or wet gas. So let's change our temperature again and assume that the reservoir temperature was about 70 Fahrenheit. So as you see, we are now to the left of the critical point, and our initial conditions would lie in here on the phase diagram. Testing it, then we will have a decline in pressure, maintaining the temperature, and we will hit now the bubble point curve, not the dew point curve. So this is an oil reservoir, and then the first bubble will start to appear while hitting the bubble point. If you analyze the gas bubble and it shows that it is a type of gas condensate, then we have a volatile oil. And if it's a dry gas, then we will have a black oil. And I like to differentiate between these two types for modeling purposes. And we will talk about that in the types of the models and how each fluid type can be modeled with a unique and a special model. So let's keep going. And we want to know now, why do we need to predict the fluid behavior? And before we continue, if anyone has any questions or want any discussion on the slide, please stop me and open your mic, okay? So every component of the petroleum system, from the reservoir to the well bore.
Excuse me, Engineer Muhammad.
Yes.
They cannot open their mic, so just raise your hand and I will enable the mic for you.
Okay. Is it clear for everyone?
We had a question from Ahmima. She was asking what is the state of the matter above the critical point.
Okay, so the critical point represents the pressure and temperature at which the gas and the liquids cannot be distinguished. So it's a very complex, if any fluid is near this critical point, let's assume that we have an initial pressure and temperature that is very close to the critical point like that, okay? So it will behave differently and it will be very complex to model it. Because at the critical point, we will not have the privilege to differentiate whether it's a gas or oil. And actually, if we go back to the fluid types, sometimes and some references put in here a sixth fluid, which is called near critical fluids. So the near critical fluids cannot be modeled except with the equation of state. And their behavior is unpredictable. And so if we have a field that is working near critical, within the near critical conditions, then our field development plan should be changed. And we must determine whether it's initially gas or initially oil. Because as you can see on the phase envelope, just let's say 100 psi or so will change the fluid type within the temperature window of around 50 Fahrenheit. So it can be here or here. And here it's a gas condensate, while here it's a volatile oil. So it's very difficult to differentiate between them. Did that answer your question?
Yes, thank you. Please continue.
Okay. So why do we need to go all through this hustle to know the fluid behavior? And this is because every component of the petroleum system, from the reservoir to the well bore, through the surface facilities to the final processing, is governed by one vital variable, which is how the fluid properties change with pressure and temperature. As we know, as fluids ascend from the reservoir to the surface, they encounter significant pressure drops and thermal gradients. This journey alters their density and viscosity, and also the phase compositions. Therefore, accurate prediction of these changes is essential for us. Because if you are going to model something like simulation and you want to forecast, okay, you won't know the liquid percentages in a gas condensate type. So we will need an robust model to just know whether we are going to have large liquid volumes or low liquid volumes. So without a robust fluid models, we risk poor decision making for sure. And sometimes it's very serious for safety concerns. And that's why we will teach you about the fluid models. So we have two basic fluid models, which are the black oil correlations, and they are empirical correlations that relate surface measurements such as oil API, gas oil ratio, to the subsurface properties like formation volume factor and the bubble point. The black oil correlations are very fast and simple and reasonably accurate within their experimental ranges. So what is meant by experimental ranges? Being an empirical correlation, they have ranges, and we have a bunch of black oil correlations. So let's imagine together that I'm dealing with a fluid with a gas ratio around 800 and API of 33. And then I use a black oil correlation within these ranges. So it gives me good results. However, if I'm dealing with another field where the API is around 20 and gas ratio around 100, then I can't use the same black oil correlation that I used from the offset. Okay. And this is because the experimental ranges of the black oil correlations can govern the output. This is one of the cons of the black oil correlations. And another one is that there is no output composition from such models. And because of that, the equation of state are there. And the equation of state mainly used to model the volatile oils and gas condensate, because the black oil correlations fails to give us a physical meaning of how the liquids start to condense from the gases. So it can't explain this behavior. However, the equation of state can. So what's an equation of state? The equation of state are thermodynamic models used to predict the fluid behavior based on their composition. And by the meaning of composition, and please pay attention because this is very important, we mean that we'll have to define the mole percent and the critical properties. And what's the critical properties is the critical pressure, temperature, and eccentric factor. So without knowing the critical properties, then the equation of state will not run. The advantages of the equation of state is that it can give us the composition of the fluid at any condition, and the limitation that they have a very long computational time, and sometimes they cannot accurately calculate the density. Why is that? Because the equation of state is derived from the ideal gas law, which is said that PV equal nRT. And I think most of us know this equation. So this is the ideal gas law. So from its name, it's made for gases and not for liquids. So if you're dealing with a gas condensate and you have condensation, then the liquid will have densities. And the equation of state will have inaccurate calculations for these densities. However, we try to work around that, and we have introduced some parameters for the equation of state to accurately measure the density. Another drawback of the equation of state is that it does not respect the mass balance rule. And because of that, it has an unpredictable nature. So here is an example for Pink-Robinson equation of state, which are widely used in the reservoir fluids. This is the main form of the Pink-Robinson, as you can see, which said that the pressure is a function of a constant, temperature, molar volume, and parameter B and A. So parameter A is the base attraction parameter, and it is equal to parameter A depending on the critical properties and the alpha. As you can see, it depends on only T critical and P critical, while the alpha is a function of kappa and the kappa is a function of a eccentric factor. So if you break down these equations, the inputs that you need to run Ping-Robertson equation of state is number one, the critical temperature, number two, critical pressure, three, eccentric factor. These are our inputs, and without them, we can't run the Ping-Robertson equation of state. So for now, you know that we need to determine these properties accurately so that the equation of state can give us accurate data. Based on that, let's talk about the critical properties of heavy components, such as C7. So we need accurate definition of the critical properties for every component in the fluid. For the lighter hydrocarbons, such as methane and ethane, these critical properties are well known and easily incorporated into the model. However, for the heavier hydrocarbons, such as C7, C8, and down to C36, so we call that heavy hydrocarbons. The bond between them gets complicated. In the lab, the composition analysis typically reports individual carbon number. So it will give us something like that. Let's see. Yeah, something like that. C7 equals around 4%. This is what the lab reports get us. And here lies the problem. Each carbon number, say C7, actually includes dozens of isomers. These isomers have a very different critical properties related to each other. Yet the lab only gives us a lumped number without any information about the isomer distribution. So because of this, we cannot assign accurate known critical properties to these reported components. And that's why this uncertainty is one of the main sources of error in the equation of state. So to explain what is an isomer, as you can see on the slide, different compounds that share the same molecular formula, but different chemical structure, and consequently different properties and critical parameters. So to give you an example for that, let's relate to C4. So the C4 can be either we have 4 carbon atoms attached together, and the link is straightforward like that. So this is the normal structure of the C4. While this is the isomer of C4, as you can see, there is a difference in the structure between these two examples. So what makes it very difficult and more complicated that the T critical here and the P critical does not equal of the isomer. So this makes the fluid more complicated. We don't know the composition of the isomers, and so we don't know the critical properties that should be assigned for something like C4. But when we are talking about pure components or components with a low carbon number, then the number of isomers will be small. So as you can see here in the table, C6 have around 5 isomers, while C7 has 9. Going down to C10, you will have 75 isomers. Then the C20 will have 366,000 isomers. So as you can see, it's becoming complicated, and the number of isomers are increasing exponentially with the carbon number. Instead, the lab simply reports something like, as we said, C7 equals to 4.5%. This is what the lab gives us, okay? It doesn't state that the normal C7 is around 2%, and then isomer number 1 is around 0.5%, isomer number 2, no, it doesn't give that. It gives us a lumped value. So actually, we don't know the critical properties of the heavier hydrocarbons. So because of all of these limitations, we must create something called pseudo component. And by the meaning of pseudo, it's a fake. So let's put it that way. So a pseudo component means a fake component. Instead of treating each carbon number as a true chemical species, we group them into a pseudo component based on the boiling point ranges or molecular weight ranges. For each pseudo component, we assign the average properties in a way that it gives the same behavior of the heavy and tail of the composition. So what we want to do that to assign a fake component and then give it the lump of the mole percentages of the heptanes. So here are the heptanes. This is the C7, the start of the C7. We know that the C7 have around 9 isomers, and as you can see, the lab reports only 3. So we have here uncertainty. So from there, we lump all the composition together. Okay, let's say it's around 30% when we sum all the mole percentages below the C7. And so we have the mole percent of 30%, and we need to assign the critical properties. So what we are going to do is that we are going to calculate the critical properties based on the molecular weight and specific gravity of the tail. And the molecular weight and specific gravity can be got from the lab because the liquids represent heavy components, and most likely from C7, they form the liquids. So we know that if we have the molecular weight and specific gravity of these liquids, then we will have the molecular weight of the heavier hydrocarbons. So from the molecular weight and specific gravity and boiling points, we will get the critical properties, which is TC, PC, and eccentric factor. And from that, we will monitor the equation of state, whether it can give us a good API gravity and gaseous ratio that matches the fluid type or not. So let's repeat that again because this is a very important point. The goal is to capture the real behavior of the heavy tail of the fluid composition. And because of that, the heavy end that controls the liquid phase behavior, which are represented by the C7 plus fractions, can match the API gravity by controlling the overall fluid density and also the gaseous ratio and saturation pressure. So we must tune them carefully to match the laboratory measurements. And this ensures that our equation of state behaves like the real reservoir fluid, even though we do not have a detailed knowledge of the true heavy end composition. So this step is called the pseudo characterization, and you can do it on softwares like the PVTP or PVTI, which are specialized in the equation of state modeling. So in simple terms, the lab gave us C7 through C36 mole fractions, but without isomer details. And as you can see, this is a lab report, and we don't know the mole percentages of all the isomers. So without knowing the isomers, we cannot assign correct critical properties to each carbon number. And based on that, then we lump the tail into a pseudo component with an estimated average properties until it gives us a match, a good match on the API, the gaseous ratio, and the saturation pressure. So how it works on the software, the first thing that we need to do is to get the composition from the lab. So we take a sample from the field and then take these samples to the lab to do recombination to assure that we have a representative composition of the actual reservoir fluid. And we do some experiments on them, such as CCE, differential liberation. And from that, we QC the lab data to ensure that everything is consistent. Then we start to define the pure components. And as we said, the pure components, we know the mole percent, such as methane and ethane. We know the mole percent, and we know the critical properties of them because this is a very known critical properties. And then start to define the unknowns and lump them so that we can define the pseudo component. And here is the trick. Before we continue with the equation of state, we must make sure that the pseudo components can represent the fluid tail, okay, by a good match on the API and gaseous ratio and saturation pressures. Then we start to enter the lab data so that the equation of state can compare its results to the lab data. And finally, we do the equation of state validation. So here's an example of the equation of state validation. And as you can see, this is the equation of state properties. And with the green positive sign here, this is the lab properties. And they both have the same track. So we have a robust model of equation of state that can predict the oil density from CCE. Also, from the equation of state, we can draw the phase envelope. And here lies the bubble point from the CCE experiment. And as you can see, it lies on the bubble point curve. So actually, this equation model predicts actually the real behavior of the fluid. And we can simulate also the separator. And from here, we can get the API and the Gazo ratios. I would like to thank you all for listening to me, and I hope that you understood most of my words. So let us open the questions right now, and if anyone wants to discuss anything, I'm here to help.
Thank you, Andrew Muhammad, for this fruitful session. I really enjoyed it. But we will take just 3 minutes break until the attendees fill the feedback form that I will send in the chat box. And then we will start receiving the attendees' questions. Okay, we will be back after 3 minutes after you fill the feedback form. So prepare your questions. Okay, it's 1 minute left until we start to receive your questions. Please fill the feedback form until this minute ends, please. Here in the I've sent the link in the chat again. Engineer Omar Khalilov. Okay, let's start receiving the questions. So we have the first question from Engineer Adam. He wants to know, he wants you to explain the eccentric factor.
Okay, so can you hear me right now?
Yes, we can hear you.
Yes, okay. Yeah. So the eccentric factor, let's put that it's that way. So the ideal gas law has so much assumptions. So it said that PV equal nRT. It has four main assumptions, and one of them that all the molecules act like spheres. And this is actually does not occur in the nature. So we know that as long as we are getting heavier in the carbon number, the atoms tends to be more spherical, more elliptical than spherical. So by that, we introduce the eccentric factor, which means and measures the degree of ellipticity or sphericity of the molecule to cure the assumptions of the ideal gas law. So it's the measurement of the degree of sphericity of the molecule.
Okay, thank you. We have a question from Engineer Muhammad. What is CCE stands for?
Constant composition expansion. Constant composition expansion. And this is an experimental that is done in the lab.
Okay, thank you. We have another question from Engineer Okan. Can you explain what is binary interaction coefficient?
Okay, so if you remember the Ping-Robinson equation of state, this form is for pure gases, okay? This is for pure components, where we are talking about a single component, not a mixture. If we start to talk about a mixture, then the mixing rules should be applied. And when we are talking about the mixing rules, so the A parameter, which stands for the attraction term in the Ping-Robinson equation of state, will have mixing rules here, okay? So it will be something like that. And in order to model it, then they have introduced a binary interaction coefficient, which stands for the intermolecular forces between two dissimilar molecules. So let's say that we have C1 and C7 molecule, okay? So the intermolecular forces between the C1 and C7 is different if compared to C1 to C1, right? So the binary interaction coefficient makes these calculations.
Okay, thank you. So, any more questions? We have a question from Engineer Hassan. He needs more clarification about the isomers part and assigning the right critical properties to right SCN.
I'm sorry, I didn't hear it right. Can you repeat
Okay,
it again?
I repeat it.
Yeah.
He needs more clarification about the isomers part
Okay.
and assigning the right critical properties to right SCN. I don't know what SCN stands for.
Okay. So I will try to make it more simpler. So what we have, that we have pure components, okay, and pseudo components. And what pseudo stands for is fake. So let's put it in that term. So it's a fake component, okay? And why do we introduce a fake component to the composition? So as you can see, this is a lab report, an actual lab report for an oil reservoir. And here it defines that the methane have a mole percent of around 40, and then the ethane, which is C2, around 13.8, and so on. When you come to the C4, the lab report defines two components, not only one, and this is because the isomers. So what is an isomer? We know that the C4 contains 4 carbon atoms, so it's something like that. This is the bond between each carbon. So what happens when we change this bond to be something like that? Do you see the difference between these two structures? They are two structures that have different properties. So we know that the I-butane will have T-critical and P-critical values that is different from the N-butane, okay? So we'll have two critical values for the C4, one that describes the I-butane and the other for the N-butane. When this is for C4, so when it comes to C5, we will have 3 isomers instead of 2 because we will have another carbon atom in here. And so we can change the structure. And as we keep going on, and as the number of carbons increase in this in our mixture, then so on the isomers. So this table describes the number of isomers for a single carbon number. So as you know, that C6 have 5 isomers, so it have 5 different structures. And these 5 different structures have 5 different bonds between the carbon molecules. And if we go to the C10, we have 75 different isomers. So we have different 75 structure for the links. And based on that, we will have to define 75 critical property, each one for each structure. And this is very difficult. And the lab cannot give us all the isomers that are there in the composition. So that's why we assume that we have a pseudo component. Okay? This is an assumption, which is a fake one. It doesn't occur. And this pseudo component has a mole percent which is equal to all the mole percentages of the heavy molecules. So if we assume that we have here 10% of C6, 9% of C7, 8% of C8, 5% of C10, okay? So when we sum all these mole percentages, then we will get the pseudo component mole percent. So let's say it's around 30%. So the pseudo component has a mole percent that represents 30% of the whole composition. And what we need to do is to assign the critical properties for this pseudo component. So here comes the problem. Where should I take the critical properties? From where? This is a fake component that I am just introduced inside the equation of state. So in order to assign the proper critical properties, we go to the molecular weight. So we have the molecular weight and specific gravity of the C7 plus fractions, and the lab can report it. By doing so, and with some correlations, we can get the critical properties. So we assign critical properties to this pseudo component. And our composition now is consists of pure components until the C7, and then there is no C7 here or C8 or C9. There is only pseudo component. So the equation of state can run now because we introduced the pseudo component, which is equal to the sum of compositions of all the heavy molecules. And based on that, we will have some results from the equation of state, such as the oil API and gas oil ratio and saturation pressure. And the deal is that if we match the API and gas oil ratio by this equation of state, then we have the same behavior of the real composition. So it works like that. And we call this step pseudo characterization.
Thank you. So we have another question from Engineer Khalid. He was asking, what is bi-interval?
What is what? I'm sorry.
Bi-interval or BI interval?
Do you mean binary coefficient? This term?
Yeah.
Okay. So we answered that. But anyway, the binary coefficient measured the intermolecular forces between two dissimilar molecules. So if we have methane, C1 and C7 heptane, then the interaction forces between these two molecules will be different if we compared it to C1 with C1 or C2 with C2. So the binary coefficient calculates the change in the intermolecular forces. And actually, to put it so simple, guys, the eccentric factor and the binary coefficient, and there is another term which is called the volume shift, they have a single goal, is to be coefficients and multipliers so that the equation of state can produce the same results from the lab. So let's put it like a correction factors that we are using and playing with it so that we can simulate the lab data.
Okay, thank you. Question from Odoya. He's asking, when do we have to make a PVT modeling? Is it before drilling or in production or simulation?
When what, please?
When do we have to make a PVT modeling?
Yeah, of
Are
course.
they carried out before drilling
So,
or when?
yeah. So the PVT model is a common input in all the simulation studies in the reserve estimation models, also used in the facility designs. So we need to develop the equation of state model after producing and testing of the field. So if we have an exploratory well and we started testing, let's say we are going to do a DST test, then during the DST test, we should get some samples from the well and then send these samples to the lab so that they can do compositional analysis. And after they do the compositional analysis, we take the composition from them and start to model the PVT. So to answer that, of course, it's not before the drilling, it's after the drilling and while testing the well. And the sample that we should take from the field should be from the first day of production. So it's not recommended to take samples from the well when it has been 6 months producing, because we are risking that we fell below the saturation pressure. And if we take samples below the saturation pressure, and by the meaning of saturation, it's either the bubble point or dew point, then we'll risk that we will have a wrong composition that does not describe the initial phase that is occurring in the reservoir.
Okay, thank you. I think this is all for today. Thank you, Engineer Muhammad, for this great session. I really enjoyed it and it was very informative. I just want to highlight two things for the attendees. There is no attendance link. You just join through website and the certificate will be generated automatically tomorrow. On the webinar page, you will find a view to my certificate option, and when you click on it, you will get your certificate. Here's a kind reminder of, wait 1 minute. Here's a kind reminder of our next live course, which will be presented by the same instructor of today's webinar, Engineer Mohammed Ala, titled PVT and Equation of State Fluid Modeling. It will start this Saturday, 3rd of May. It's a 1-week course. Its original price is $200, and you will get it for only $180 for the first 5 registrants. After, you will get 10% discount if you get the early bird discount. So you can also you can scan this QR code or just visit the website and you will find the course on it. So thank you for attending, and see you soon, inshallah, in our next webinars. We have one last question before we end up our session from Khaled. Can we predict the MMB from equation of state? If yes, so how?
Yes, we can. You should develop the equation of state model first, and then you can find the minimum miscible. Yeah, you can do it, but you should first develop the equation of state.
Okay, thank you. Thank you again for this session, and thank you all for attending. See you soon, inshallah, in our next webinars.
Thank you, Mr. Adel.
Thank you.